Okay, let's get started. So to remind you of what we were talking about last week, we were talking about alkanes, the nature of alkanes and how we name them. So just to remind you that we have a systematic way to name alkanes, looking for the longest chain of that molecule, that's the parent of the molecule, and then finding the substituents and naming them and putting numbers. And there are more details in terms of these specific steps to go through. I've just summarized them here. But in general, this is the process that you would go through to determine the name of a molecule. For example, this one we showed last time in class, where you identify what the longest continuous chain that's most branched is, identify the different groups that are branching off of that chain, and name them according to their substituent name, and then number it to give overall the lowest number, starting from the end of the nearest branch. And then we can name the molecule. So hopefully you have no problems with naming. If you've done some of the problems, you should have been able to practice that. Okay, we talked about how molecules are always in motion. And it's sometimes very useful to analyze specific frozen conformations of that molecule and get an idea about the shape, the energetics, the arrangement of those atoms. Because in some molecules, those conformations do affect the way they react, and they affect the way they interact with other molecules. Conformations of molecules are very important in how biological molecules in biological systems interact, because that three-dimensional shape is critical for recognition of one molecule by another. For example, an enzyme recognizing a protein substrate has to be in the right conformation. But to remind you, conformers, or different rotational isomers, it's not that at room temperature or at even at lower temperature that you don't have multiple different configurations of a molecule as bonds rotate. You do. Typically, you don't see different conformations frozen out until you're at very low temperatures. However, in some cases, those energies are high enough. And I think when we see some examples of six-membered rings, cyclohexane conformations, we do see conformations where it's because the energy is so high from one to the other that it will favor one, and that's all we see. So remember, conformations, we're talking about taking a snapshot, a frozen picture of molecules that are always in motion. Bonds are always rotating if they can rotate. We looked at the conformations of the simplest organic molecule that can undergo rotation. That's the 2-carbon ethane. And as you rotate one carbon relative to the other along that bond, we can analyze all the different interactions from the groups on one side of that carbon and the other. So if you recall from Thursday, we looked at different ways to view the conformations in the sawhorse view, and then if we look down the axis of the carbon-carbon bond, we can get a projection of that, trying to represent this on a two-dimensional page that looks something like this. Okay? So you can get the relationship of the hydrogens that are closest to you on the carbon closest to you to the hydrogens that are on the carbon furthest away from you from your viewpoint. And you can see as you rotate, as that bond rotates, those bonds on the front carbon and back carbon start to overlap or line up, so-called eclipsed. And the atoms, actually, hydrogens are relatively small, but as we get larger atoms, then we see steric crowding. So those two things lead to higher strain in the molecule. And if you were to plot the energy of that molecule as that rotates, you see some slight differences. It's not great, not huge, but is significant enough sometimes to affect reactions. To about 3 kilocalories per mole from the conformation that I have on the left here to the fully eclipsed conformation that I have drawn on the right. Okay? And notice if you rotate around a fully 360 degrees, since all of the groups that are on these carbons in the front and back are identical, all of these are hydrogens, okay? If you rotate, you'll get to an eclipse where you have all the hydrogens across from each other and then staggered, eclipse, staggered. But the energy for each of those different rotations, all the way around 360 degrees, would be the same. So if you look at the eclipse conformations, they're identical. Okay? That's not the case when you have larger molecules with more things on it. Move forward. These strain energies that come into play, especially the steric strain, if we have larger groups, like in butane, now we have a different relationship between, if we look specifically at this 4-carbon butane, a different relationship between the groups if you're looking at the middle 2 carbons and down along that axis, as I've represented here. So in this case, we have this particular conformation of butane where, again, looking at the middle 2 carbons, we see a larger group and 2 smaller hydrogens on one side, a larger group and 2 smaller hydrogens on the other side of our view. And here they're furthest apart. But if you rotate that, they come closer together. Okay, so if you plot the energetics of that, it looks something like this, where you have one conformation which you would expect to have the minimal amount of strain in it, torsional and steric strain, that's here. Okay, as you rotate, you eclipse those bonds, so you get this electron-electron repulsion that increases the energy of the molecule. That repulsion, torsional strain, for that conformation shows up here. Okay? If you continue rotating to get to this third conformation, you relieve that strain from the bonds being eclipsed. Right? So you go down in energy. That's what's shown here on this graph until you get to the staggered conformation. But it's not as low energy as you started with because look what's close together here. These CH3s are closer together. Okay? And then if you continue rotating, those CH3s are actually bumping into each other. That gives us the highest energy. And then you continue rotating, you essentially see a mirror image of the other side as you go through those energies. So does anybody have difficulty understanding how the energy of a molecule actually fluctuates as we undergo bond rotations?
I have a question.
Yes?
So as you're like increasing in energy,
Mm-hmm.
and then obviously rotating, does that mean it's going to decrease in the strain?
Well, if the energy is going up, you're getting more strain. It's becoming less stable. Okay, does that make sense? More strain, yes. So your higher energy, less stable, more reactive, more strain. So all those things sort of go hand in hand. Good question. Okay, now, let me just back up one more time. Now notice when I looked at this specifically, this energetics of butane, that because of the steric strain of the groups where they're rotating, notice it's really high when they're pushed together. Because of that steric strain, that makes longer chain alkanes most stable, the lowest energy, the most stable, when it's in a completely staggered open form. So if you look down any 2 bonds in this molecule, here, here, if you were to look down this bond, if you were to look down this bond, you can analyze the rotations around any 2 carbon-carbon bonds in this molecule and look at those relationships. The most stable conformation for linear alkanes is this fully open, extended, staggered conformation like I've drawn here. You can see in this case, with the stick model, if it's twisted, and certainly it does twist, but there's more. For example, if you look at that group and that group along those 2 carbon-carbon bonds, they're close together. So being completely open and extended would certainly be the better situation for it. Right? Now, all of these different types of rotations of the molecule, there are many ways in which this molecule can move around. All those bonds are rotating, and at room temperature, there's enough energy for them to rotate rapidly. And so the molecule is just kind of, I don't know, twisting and turning, and as much as the degrees of freedom allow it to rotate. Okay, that's true for these linear alkanes. If you think about molecules now that are no longer linear, like in cyclic alkanes, because you can imagine having a chain of carbons and then joining the ends of that chain, you can make ring compounds, what we call cycloalkanes. Okay, here's some examples of cycloalkanes. The smallest, of course, is the free carbon ring compound. Notice the name that we use for these. So when we name these molecules, we use the parent name for the chain. In this case, free carbons would be propane, and we put cyclo in front of it to refer to the ring structure. Okay, so we can have molecules which are 3 carbon rings. Yes, question?
So this might be, you might be getting to this yet, but let's say you have that cyclopropane, and then you have like a butane branch coming off of it.
Yeah.
Would that still be the root then, the propane?
The question is, if you have a cyclic ring and a branch coming off it, which is the parent chain that you use for the name? And the answer is whichever is longest. So if the ring equals the same number of carbon as your branch chain off of it, then the ring gets priority for the parent. If the carbon chain is longer, has more carbons than the ring, then the ring is the substituent and the carbon chain is the parent.
But you can't count carbons on the chain and in
No.
the ring. They're
No.
two separate.
No, they're 2 separate things. So, yeah, I'll draw some examples here in a minute. But notice if we go from 3 carbon to 4 carbon to 5 carbon, 6 carbon, and so on, cyclobutane, cyclopentane, cyclohexane, we can draw them in the line structures like this. If you have substituents here, in this case, in these examples on the bottom, those substituents on the ring are smaller than, less number of carbons than the ring. So in this case, we simply call this methyl cyclopentane. Okay? Because the parent cyclopentane encompasses all of those 5 carbons in the ring, and then the substituent is the additional carbon from that CH3 group. Okay? Now why don't I need a number here?
Because no matter where you put that methyl group, it's going to be the same.
That's right. No matter where you put the methyl group on the ring, if you just have one branch off of a ring, it doesn't matter. Every place you could put it, you would just call that the number 1 position. So you don't need a number if it's completely unambiguous that there could be no other possible compounds. But compare that to the second case here, where I have the 6-membered ring. So the parent here is cyclohexane. That's that ring. And we have 2 substituents. Now we have to put numbers because they are arranged around the ring relative to each other. Okay? So in this case, at one of these points, you start numbering 1. And then you number around the ring towards the direction of the closest branch. So let me clean this up a little bit. So here we would say number this carbon number 1. That's 1. That's right there. This would be carbon number 2, because that's going in the direction of the nearest branch. This is carbon 3, 4, 5, and 6. If we number the other way around, those numbers would be bigger. You'd start 1, and the next branch wouldn't be until the 4th carbon away. Okay, so something to add to your rules on naming. When we go to cycloalkanes, again, we want to go in the direction that gives us the smaller numbers. Okay, and in this case, obviously there are more things here. So carbon 1, 2, 3 on the ring, cyclohexane. We have 2 methyl groups attached to what we've started as number 1, and then the ethyl group on carbon 3. Okay, so then hopefully this makes sense, right? Anybody confused about how we're doing this? Okay, so the question that came up about whether you have other, let me just wait this. If you have other chains, for example, let's just say we have something like this. 1, 2, 3, 4. Ooh, that's terrible. Okay, how would you name that molecule? Yeah, it's 7 carbons, so this is a heptane. The ring has 5 carbons, so that's a smaller number of carbons. So heptane is the parent chain. Heptane. So now we have then heptane. The word heptane encompasses all of the carbons of that 7 carbon chain. So make sure when you name things, you're not ever double counting the same carbons in substituents and the parent. The 5 carbon ring encompasses all of those carbons. Okay, so it's attached to the heptane chain at carbon number, what? 4. And it could be attached anywhere along there. And this happens to be then 4, how would I name this as a substituent?
Cyclopentyl.
Cyclopentyl, exactly. 4-cyclopentyl. Oh, sorry, this shall be one word here. 4-cyclopentyl heptane. Cyclopentyl is the substituent in heptane, and it's on the number 4 carbon. Okay, so that's how you would name something like that. The biggest, the most common mistake I see when people name things is when they have rings in it, is they either forget to put cyclo or they put it with the wrong R. They put it with the heptane or not the pentyl and things like that. So be really careful you don't make those kinds of mistakes. I see that very commonly. Okay. So any questions on naming alkanes with ring structures? Yeah.
So if that cycloalkane was attached directly to the instead of having.
Oh, okay. So you're thinking of it was if it was. Let me see if I can. So you're thinking of something like this.
Yeah.
What's the longest chain? If it's joined like that, these are 3 carbon chains coming off of the cyclopentane. So the parent here would be the cyclopentane ring. This would be the parent, including that carbon. And then these are 2 ethyl groups. 2 propyl groups. Propyl. Dry. So you have 2 propyl groups. So this is just 1,1-dipropyl cyclopentane. Okay. So 2,2-dipropyl cyclopentane. Yes, question?
On that bottom right hand one, the 3-ethyl, 1,1-dimethyl, could you have certain numbering from the ethyl group? So 1-ethyl, 3.
It would describe the exact same name, the same structure, but it would overall give higher numbers, and that's what we want to avoid. So if we did 1-ethyl, 3,3-dimethyl, now we have 2 numbers with a higher one. And so we usually opt for the lower one. Okay, and there are some more subtle little rules that even I sometimes forget. So if you did it this way, would I count that wrong? No, it describes the exact same structure. So I think if you at least can get the exact same structure without being really, really wrong, I'm not so worried. But yeah, technically you want to try to get the lowest numbers overall. Okay, now there's something else that happens that we have to be aware of with ring structures. So let's take a close look at the simplest, smallest ring structure, cyclopropane. Okay, here's the 3-membered ring. This just happens to be cyclopropane with all hydrogens on it that I've drawn there. Okay? And now I have a structure where I have two groups off of that ring. So I have 1, 2 dibromo in this case. Could be methyls, it could be something else. Cyclopropane. Okay. Now remember I told you that whenever we have carbon-carbon bonds, they're always rotating, right? Rotating rapidly. In all of those butane, hexane, pentane, linear alkanes, those bonds are constantly rotating. But what happens if you take these rotating carbons and tie it up in a ring? It's no longer possible for those bonds to rotate. And that's something to be aware of. If you look at this cyclopropane structure, and you look at this carbon-carbon bond, because it's attached back here, there's no way that this can rotate around. The whole molecule could tumble, but that's not rotating the bond, this carbon relative to that carbon, right? So when you have a ring structure, you're actually fixed and restricted. And so there are differences when you have groups attached on the same side of that ring versus on opposite sides of that ring. So what I've shown here in this dibromo cyclopropane structure, I didn't really indicate any indication about the three-dimensional positions of those bromines. Okay, well those bromines could be attached on the same side of the ring or on opposite sides of the ring. Okay, and that leads to different isomers. Because they're not the same molecule. They have different properties, they have different positions in 3 dimensions, and there's no way you could interconvert them by bond rotations. So they're not conformers, they're actually different isomers. But a different kind of isomer. Remember the definition, what's the definition of the sort of broad definition of isomer? Molecules which have the exact same number and kind of atoms, but somehow are different molecules. That could be different because they have different connections, like we looked at constitutional isomers earlier. They're bonded together differently. Well here, all the atoms are bonded to the same atoms. Yeah, we have different molecules because there are no way you can interconvert them without actually breaking a bond and changing to positions. But this is only a difference in 3-dimensional orientations. Something we call a stereoisomer. I think I have that defined on the next slide for you. Stereoisomer are 2 different isomers which are only different. They're all bonded to the same atoms, but they're different in 3-dimensional space. And we have to be able to distinguish them with a naming system. And so this is where this additional term comes in when we refer to a trans 1,2-dibromocyclopropane versus the cis 1,2-dibromocyclopropane. Because that refers to the relative positions of 2 groups. So trans meaning opposite sides. So in this case we have 1 bromine on top of the ring and 1 bromine on the bottom face of the ring. Okay, that's what we refer to as trans, opposite. Okay, and the word cis refers to both these bromines being on the same side of the ring. It's on one face of that ring. Cis meaning same. Okay, so that actually, we add that to the name to distinguish the 2 possible stereoisomers that could result from having the exact same connections. 1 bromine on carbon 1, 1 bromine on carbon 2. But because now there's no way for the carbon-carbon bonds of the ring to rotate around freely, they are fixed in space. Okay, does that make sense? So trans, opposite, cis, same, and we use that in front of the word, in front of the name, to indicate which stereoisomer we're talking about. So here you go, stereoisomers. Isomers that have all the same number and kind of atoms, and they're all connected to the same atoms, but they're different in their arrangement in 3 dimensions. Okay? Different in 3 dimensions. Everything else being the same. And so because of the ring restrictions of rotations of carbon-carbon bonds, they're stuck in one particular orientation. Okay, so cis and trans. Here's a cyclopentane. Now, when you have larger rings, of course, you can have those groups in different positions. You can have 1, 2, you can have 1, 3 in terms of a cyclopentane. Here is how we would represent on a sort of a flat, trying to draw a flat structure picture. We would use wedges and dashes to indicate whether they're on the same or opposite side. So here, for example, I've drawn just the flat ring structure and showed these bold wedged lines indicating they're both coming up out of the page, right, up towards you. Since they're both on the same side, same face of the ring, we would refer to that as the cis structure. And this is trying to give you a perspective looking sideways at the ring. So we can have the cis 1,3 dimethyl cyclopentane or trans 1,3 dimethyl cyclopentane. Different molecules, different stereoisomers, but have the same kinds and atoms all bonded to the same atoms. Okay, so any question about cis and trans? Now, I've drawn these structures all flat, and I want to come back to this issue of strain for a moment. Whenever bonds on carbons that are adjacent and the bonds coming off eclipse each other, as we saw in those conformations, there's electron-electron repulsion and torsional strain. Whenever you have large groups, you have something called steric strain that bumps into each other. Now when we have something that shows up a lot in ring compounds, which adds even more strain to the molecule, something we call angle strain, in addition to those other two things. An angle strain is a result of having to, because of the size of a ring restriction, forcing bonds to be at non-optimal angles, smaller or larger. If you have like in a tetrahedral carbon, right? What's the optimal bond angle for a tetrahedral carbon between any of the two bonds? 109.5 degrees. That describes a perfect tetrahedron. Well, if you have to squeeze that bond smaller than the angle or spread it out larger than the angle, it's not optimal. It's more unstable, and it adds some more strain energy to the molecule. And when we have ring compounds, we can analyze each of these different kinds of strains, and we see added strain due to angles not being optimal. And all together, we refer to this as ring strain. Ring strain. And it's important to understand, I think, looking at the three-dimensional conformations of ring compounds, how these strains develop. Now, if you were to take a series of cycloalkanes of different ring sizes and burn them and measure the heat release and then normalize all that to the same number of carbons and hydrogens so you can directly compare, and what we can see out of that is the energy, the extra energy of the molecule just due to the ring strain is different with different size ring compounds. So the most strained or the highest energy cycloalkane, and not too surprisingly, is a 3-membered ring. So if the number of carbons in the ring is 3, it's the highest energy. If you go to a 4-membered ring, a cyclobutane, there's a little less ring strain in that molecule. A little bit, not a lot. A little bit of less ring strain. Okay, and that's what this energy picture is comparing. A cyclopentane, what we find is that the strain energy due to being in a ring versus being an open chain is lower than a 4-membered ring or a 3-membered ring. And when we get to a 6-membered ring, it's actually there is no strain associated with being fixed into a ring versus an open chain. There's no extra strain. Okay, no ring strain. That's the lowest energy. Then we go to 7, it actually goes up a little bit. 7, 8, 9, and then once you start to get really large rings, then there's more flexibility in that molecule to be able to adopt conformations that remove all those strains. But if you're a small ring, it's forcing the molecule in very specific conformations that can't move. Okay, that increase that strain. So let's take a look at actually what those ring compounds look like in 3 dimensions. Well, the cyclopropane, actually, if you were just to look at 3 carbons that define a ring, right, that would be a triangle. And the bonds would have to be 60 degrees to form a carbon-carbon bond of a cyclopropane. Okay? Actually, even 60 degrees compared to what it wants to be, if these are sp3 hybridized, 109.5 degrees, that's a huge difference from what the optimal angle should be, right? Huge difference. That's why the 3-membered ring has the highest amount of ring strain, because angle strain makes up a huge amount. So much so that if we actually calculate the orbitals and how they overlap, they're not perfectly end-to-end. They actually can't even adopt 60 degrees. They're actually bent a little bit. And so it's not optimal overlap. So not only does a cyclopropane have a lot of ring strain, the bonds are weaker than a typical alkane carbon-carbon bonds because they're not optimally overlapped. They can't be. So I've sort of drawn in yellow here sort of how the sigma orbitals are not perfectly overlapped linear end to end. Okay, you can't really follow the dimensions of the 3 carbons. Okay, so what would you expect then the shape of the molecule to be? 3-dimensional shape for a cyclopropane. Carbons and hydrogens. Well, it's flat. 3 carbons define a plane, right? 3 points would define a plane. And if you have the smallest possible ring structure with 3 carbons, those 3 carbons all have to lie in the exact same plane. There's no other possibility. So if you look at the sort of these representations here, and I've shown the cyclopropane a little bit tilted here, so you can see the carbons on the ends. If you're to actually look exactly sideways, and again, I want to try to relate this to a Newman projection. If you were to take your eyeball here and look down, say this carbon-carbon bond between those 2 carbons, and look at this side view, that's kind of what I'm showing here. So if you imagine a Newman projection where we have this, and then the carbon behind, and the bond behind. What else do you notice about cyclopropane? Besides being flat and having really, really small angles, so angle strain, what about torsional strain? Would it be high or low? Remember, torsional strain are when bonds from adjacent carbons eclipse and overlap. With cyclopropane, every carbon-hydrogen bond here is overlapped or eclipsed with the one behind it. Okay, here, here. If you were to look down these bond angles too, you'd see those would be eclipsed, those would be eclipsed. So all of those bonds are eclipsing. That also adds to the energy of cyclopropane. why it was the highest energy of the ring compounds. You have the highest amount of angle strain, you have the highest amount of torsional strain, so of any of the ring compounds, because it has no choice but to be stuck in that position only. There's no rotation possible. Does that make sense? Hope you're able to visualize this. So it's no wonder cyclopropane is the highest. Let's take a look at cyclobutane. We've added one more carbon to the ring. One more carbon to the ring. And just that one additional carbon, because to try to get more optimal angles as much as it can, it's not completely flat anymore. If you notice the picture on the right where I've tried to show a side view, what you see is that the four-member ring is slightly puckered. It doesn't want to be flat because that would be just like cyclopropane, maximizing all of those strains. So by slightly puckering its structure here, it allows a little bit of angle strain relief. And notice, if you look down this bond angle, notice those are not completely eclipsed anymore. They're not completely 60 degrees apart, but they're slightly apart, trying to relieve some of that torsional strain. So the molecule will adopt a conformation which will try to relieve as much strain as possible, and the four-membered ring no longer is completely flat. But you know, to remember from the energy chart, it was a little less energy than cyclopropane. It's because it can pucker just a little bit. It doesn't relieve a lot of that strain, because it can't move that much, but it can move more than cyclopropane. Okay. How about cyclopentane? Notice, remember from the chart, cyclopentane drops significantly in energy. Well, here's cyclopentane. Again, not everything is perfectly aligned. However, with the additional carbon, it puckers even more, what we refer to kind of like an envelope conformation. So if you look at the ring, you have one carbon significantly out of the plane defined by the other carbons. And that relieves, again, if you look sort of down this Newman projection, look at the angle here. Not completely staggered, but significantly more than the cyclobutane. Okay. Now we also get to a situation where it can wiggle a little bit. There's no free rotation because the ring restricts that, but it can wiggle a little bit. So molecules can move a little more as the rings get larger. All right. Take a look at that energy graph again. When we go from a 3-membered ring to a 4-membered ring to a 5-membered ring, significant drop in the energy because we've relieved quite a lot of that strain. And then we get to sort of this magic number 6. If you look at the ring strain associated with any torsions or bond angles for a 6-membered ring compared to an open linear alkane, it has no additional strain from the ring. That's what being 0 on the graph means. No additional strain from being in a ring versus an open chain. And so what that tells us is that a 6-membered ring has been able to minimize all of the torsion, all of the angle strain, as compared to, and be just like a linear alkane. And then as you go larger, you increase that. Why is that? Why is that minimized? Well, let's take a look at the structure of a 6-carbon chain ring. I have color-coded the hydrogens here differently for a reason I'll explain in a minute. But if we look at the 6-membered ring, there's now enough carbons that we can pucker the molecule out of plane so that the bond angles are optimal and the same as if it were an open chain. Okay, so the bond angles are not particularly strained because it's in a ring. Okay, so if you look at the end-on view, the other thing you notice, and if you look again down, if you look at any two carbon-carbon bonds, any of the carbon-carbon bonds on cyclohexane, what you see, again, if you could imagine this as a Newman projection, you see that these are perfectly staggered bonds in the front and in the back. They're perfectly, from the front to back, 60 degrees apart. So the torsional strain is minimized. The angle strain is minimized. And this is the most stable of the ring structures, of these sort of small, medium ring structures, size structures. Okay? Because it can adopt this conformation, it becomes more stable and lower energy. Now, I should tell you what we refer to this as. Notice the shape of this ring compound is not flat. It's puckered, say, up on one end and down on another end. It kind of resembles a lawn chair, if you will. And so we refer to this as a chair conformation, the cyclohexane chair conformation. Okay, in this orientation. Okay, so take a look at this picture, this sort of three-dimensional representation for a moment. And notice the different colored hydrogens I put on there. Now each carbon has two hydrogens attached, right? Every carbon in the ring has two hydrogens attached. But they're oriented in different orientations. If we look at this sort of side-on view of cyclohexane, what you see is that alternating every other carbon, there's a hydrogen which points straight up, then straight down, then straight up, and then back here straight down, straight up, and straight down. All the ones I've highlighted as pink in this particular picture. Okay. The blue hydrogens also alternate up and down along the, I would say if you were to look at the ring as flat, there would be ups and downs, like the same side and opposite sides. This alternates also from one carbon to the next, that sort of point out away from the ring. So this, let me just do blue here. Use a blue. So here we have it sort of pointing out away from the ring. This one's pointing out away from the ring but slightly down. The one in back, which you can't see, is pointing out away from the ring, away from you. This one's pointing out slightly down, this one's pointing out slightly up, this one's pointing out slightly down towards you. Notice those are I've color-coded them because they're actually slightly different environments, those hydrogens. So on each carbon of cyclohexane, the two hydrogens are actually different if you were to freeze the molecule in this conformation. And I think as the next slide, I think I have the, looking at a top view. Yes, here's the top view of that cyclohexane, again with the same color coded. Now what you don't see are the hydrogens pointing down away from us. So if you're looking at the top, you see these blue hydrogens, this one's slightly up, pointing out away from the ring, slightly down, pointing out away from the ring, slightly up, slightly down, but all pointing out away from the ring from this top view. And we see one on each carbon, right? The pink hydrogens are alternating straight up and straight down, so we only see three of them. Here's one pointing straight up at us, here's one pointing straight up at us, here's one pointing straight up at us, alternating carbons. The ones that you don't see are pointing straight down. I'm trying to indicate that here. But hidden from this particular view. Okay? We refer to these different kinds of hydrogens as being either in the equator of the ring, those are the blue ones, equatorial, or pointing straight up or down, we refer to these as axial hydrogens. Axial and equatorial. Okay, they have different amounts of steric crowding. If they're just hydrogens, they're pretty small, but as we'll see in a few minutes, if we start to put larger groups on there, we see a significant amount of steric crowding. Notice already what you can see from this space-filling model I have on the right side, the close proximity of the pink hydrogens, even in every other carbon. They're close to each other relative to, say, these blue carbons, which are further apart. Okay, and that makes them slightly different. Okay, so does everyone have a good view of what this six-member ring structure looks like? Here's actually the molecule. It can move. There's enough flexibility in the molecule that it can flip from one chair structure to another. So if you're to look at the molecule here, where do I have it? So here, if the chair is like this, there's the head and there's the feet, it can flip. The foot goes up and the head goes down. Okay? Those are two different chair structures. And the molecule, as you go from one to the other, you rise in energy and go back down, just like we talked about conformational movements of butane or ethane. When you have ring structures large enough to be able to give a little bit of movement like this, one chair structure to the other, you go up in energy and down. I'll show you an energy diagram in a few minutes. One thing I want you to notice here, let's see, do I have it? I haven't color-coded the hydrogens in this particular movie, but what happens when you switch from one chair structure to the other, when you do what we call a ring flip, every hydrogen that was axial before, alternating every carbon, every hydrogen that was axial before became equatorial, and every equatorial hydrogen became axial. And hopefully I'll be able to show that in a minute. So in this diagram, it's a little more detailed to show you various different conformations of the molecule, but the ones that we consider mostly, there's a significant energy difference between the most stable chair structures here and here, that's what we were just seeing, the ring flipping, and any other structure in between that you could draw. Those are all higher in energy by a lot. So here, 45 kilojoules per mole. It's a pretty big difference in energy to that highest point. So when we're considering reactions and structures of cyclohexane molecules, when we're doing reactions on them, it really is these chair structures that we really need to pay attention to because they are the lowest energy ones and the most likely conformations. There's another structure, sort of a structure which we often look at where both of the ends of the chair are up or down. And that's what we refer to as a boat structure because it kind of looks like a boat. That's a higher energy structure. Sometimes when molecules are rigid and fixed, you can see those structures, but mostly not. Mostly it's the chair structure. Okay, so I want to take a couple minutes to show you a little more because what we're trying to do when we draw these structures is try to represent three-dimensional structures on a two-dimensional piece of paper or screen. Okay, and so it's important that we recognize when we draw a chair structure, without bold or dashed bonds or things that we usually use to represent coming out and going back, how do we draw them and always understand what the representation means? So let me just go through a little bit of drawing a chair structure. Okay, so to start with, one of the things you need to recognize is that in a six-membered ring, you have six carbon-carbon bonds. Okay? And when we draw a chair structure, the carbon-carbon bonds that are opposite of each other all the way around the ring So they're always parallel. So two bonds are always parallel, the two opposite the ring, the two opposite the ring, the two opposite the ring. So to start drawing a chair, what we do is, it's pretty simple. We just start with either going slightly down or slightly up, draw two parallel lines. Those are carbon-carbon bonds on opposite sides of the ring. Notice I've lined them up. Just get this. So I've lined them up. Notice they're parallel and lined up, one underneath the other. So that's how I always start a six-membered ring. Then what you want to do is draw from the left side here that I showed angling up, you want to draw a carbon down. So you have one side of the chair connected to each of those ends. And then on the other side, you want to draw the same thing, but up. Well, it's not perfect, but it's pretty close. There is our chair structure. Okay. So can you draw that? Pretty easy, right? Now, I just want to highlight a couple of things. Again, we started with two parallel lines. So the bonds I'm coloring red here, those are parallel to each other in this drawing. Whenever we draw these chair structures, it's assumed that in the ring, the lower part of the molecule is closer to us, and we're looking kind of side on. So that's always closer to us. The back is further away, or the top is further away. So this is closer, and this is away. This side. Okay, make sense? Okay, so notice those two parallel lines. What other lines are parallel in this structure? Yeah, pick any bond. Let's just take this bond that I'm coloring blue, that carbon-carbon bond. Its parallel bond should be the one directly opposite across the ring from it. Okay, so that would be this one in our drawing. Those bonds are parallel to each other. See that? The other bonds are at a slightly different angle. Let me color-coded green. How about that? So this bond that I'm color-coding green has the same parallel. It's parallel with that bond there. Can you see that? Now that's just one view. If I were to rotate the molecule, you'd see the exact same thing. They'd all be identical. And if you have trouble seeing this, get some molecular models and take a look at a chair cyclohexane and hold it and move it and see what it looks like. Okay, so that's the carbon skeleton. I wonder if I can move this over a little bit. Let's see. Center that in the page. Okay. Now, remember, on each carbon of this ring, there are two hydrogens, right? So where do you put those hydrogen bonds? This is a big problem people have until they really practice this and know how to draw this properly. Let's draw those hydrogens, the bonds to them. And remember, at every carbon, there's an axial bond going straight up or straight down, and an equatorial bond going out, away from the ring, right? So where do you start? Well, I always start at a point going up. All of the carbons that are joined with the points going up have the axial bond straight up, and all of the points with where the carbons are joined by bonds pointing down have an axial hydrogen going down. So let's draw in these 6 axial positions as we go around. Here's one, up. The next one is down. This one is up. Notice it's in front. This one's down. This one's up. And this one is down. You see that perspective, hopefully? The perspective now. Those are the axial positions. And then we have the equatorial positions. Let me color them purple for now. Now, if you think about each carbon as being a tetrahedron, again, let's start at the carbon all the way on the right, where I put that first axial bond up. Where would the fourth bond to that carbon be, the equatorial bond? It would be like this. Notice now that carbon looks like a tetrahedron, right? So I drew the equatorial bond, it's a tetrahedron. How about the bond on the next carbon down closest to us? Which direction should I draw it? Well, it comes out like this. Sort of coming out towards you in a three-dimensional picture. If I keep going around the ring, this one comes out here. If I go further, this one goes like that. This one in the back, goes like that. And then this one here goes like that. Now that's a little bit more tricky to put these equatorial and axial bonds on this drawing. It really does take some practice looking at this carefully. One thing I want you to notice about the equatorial bonds, they're parallel with ring carbon-carbon bonds. Can you see which ones are parallel with which? So notice I've color-coded the ring with parallel red bonds, parallel blue bonds, and parallel green bonds. Well, let me show you with colors now all of the equatorial bonds which are parallel with green. That would be this one. Okay, that equatorial bond is parallel with the green bond, and this one in the back on the left. That's parallel with the green bonds. Looks a little scribbled. Hope you can see that. Okay. The red bonds. Which of these bonds are parallel with the red bonds of the ring?
Left and right.
Yeah, the left and right. So this one. And that's a way to check yourself that you've drawn these in the right orientation. These relationships between all these angles to try to depict this three-dimensional structure. What's left? Blue bonds? Okay, the blue bonds, this one, and this one. So notice the relationships between those equatorial positions and the ring bonds. That's how we draw a chair. I've taken some time to go through this because I think it's important to recognize all of these different relationships to draw that should be present if you have a properly drawn chair structure with all the axial and equatorial bonds that are going out from it in the right orientations. That gives us an indication then of the three-dimensional structure of this conformation. Okay? Any questions about this? I'm going to draw one more chair and show something else. So I'm going to redraw this sort of all in one color. So I'm going to erase that. Let me just draw the chair again. Notice I've drawn it all black, but again, recognize which bonds are parallel to which. The two carbon-carbon bonds are crossing each other at any position on this ring. And I'm going to draw the axial hydrogens as pink here. And the equatorial hydrogens as blue. Okay, so that's my 6-member ring. You can tell I practiced this a lot, right? I can do that quickly. I wouldn't expect you to do that quickly. Now what happens if we undergo a ring flip? And the way to think about that from this structure is this carbon will go down, these bonds will move up, those carbons go up, these carbons shift down, and that carbon shifts up. And if I do that ring, this way, if I do that ring flip, every carbon position changes. Every axial bond becomes equatorial, and every equatorial bond becomes axial. So let me draw that and show you how I would draw that. So if I have the foot of the chair on the left side here, now that foot of the chair is going to be on the right side in the ring flip conformation. And my two parallel bonds in the middle are going to be opposite, so I'll be starting from this direction. Okay, and then that's my chair. That's the ring flipped chair. And again, every position, I'm going to keep the same colors that I started with, because what happens when you rotate is this axial hydrogen on the left that I'm circling, as those bonds rotate, it moves down and becomes in the equatorial position. Okay? And that's true for every position. So the hydrogen that was here, the ones pointing straight down, become equatorial. And this one becomes equatorial, and this one becomes, this axial hydrogen became equatorial, and this axial hydrogen became equatorial, and that axial hydrogen became equatorial. Okay? The blue hydrogens also, each one changes. So this hydrogen moved down and pointed straight down. These hydrogens point straight up. These hydrogens point straight down. And this hydrogen points straight up. Okay? So when you do a ring flip, every position inverts from its axial to equatorial. Does that make sense? Again, if you have models and you can't see that, models might help you to visualize that. I know my drawings are a mess. The consequence here is, if there are things other than hydrogens, the equatorial positions are more, there's more space there than in axial positions. Axial positions are more crowded. So there is also a difference in energy sometimes if you have different groups attached around different places. Let me show you, for example, here. If you have the cyclohexane now, which has a methyl group on it, that methyl group can be in either an axial or an equatorial position. And I've just drawn, I haven't drawn all the hydrogens for clarity, I've just drawn every other carbon to show you, because I want to point out the issue here. If you have a methyl group now in an axial position, remember that from the model I showed you before, those axial positions are close together. So there's actually some steric strain that starts to get introduced in an axial position. If we do a ring flip, where this end comes down, these bonds flip up, and that flips up. We get to this conformation, the axial methyl then moves down to an equatorial position. Okay? The equatorial position has more room, more space around it, open space, which would be less strain. Questions?
That's the same exact molecule, it's not a stereo.
These are not stereoisomers. These are two different conformations, and they can interconvert. So now we're talking again about conformations. We haven't gone from two things on the same side of the ring to two things on the opposite side. That brings up a good point, which I should reiterate here to avoid confusion. Notice on these ring structures, and I'm going to draw here also. Let me just draw these hydrogens. If we're going to draw this ring in a flat way, I would draw it like this. Okay. And if you draw any of these positions on here, you can use a bold and dashed lines to indicate coming up or going down, right? This is how we could represent the molecule. Notice the CH3 and this hydrogen are on the same side of the ring, the CH3 and that hydrogen are on opposite sides of the ring. But when I draw it like this, it doesn't indicate whether they're axial or equatorial. We know the ring isn't flat, but there's still a top face and a bottom face to the ring. So if we look at this structure of the chair conformation, okay, on this carbon that I'm highlighting red, okay, what's the top position and what's the bottom position? Pretty easy, right? Here's the up or top position if you're to look flat on the ring like this. Here's the down or bottom position. Okay. Notice up here is axial, and down on that same carbon is equatorial. Right? Go to the next carbon over. What's the up group? What's the up group and what's the down group? This one is up, right? And this one is down. But in this case, up is equatorial and down is axial. So if we actually look at, if we were to look at it flat, we would just see bold and dash coming out of the paper, going away from the paper, looking straight on top of the molecule. But if we actually analyze the three-dimensional structure, notice axial and equatorial on one side of the ring alternate. Axial, equatorial as the up positions as you move around the ring. And on the bottom, the down position, same thing. They alternate axial, equatorial as they move around the ring. So don't get confused between same side, opposite sides when we're referring to stereoisomers. If the ring were flat and we're looking on one side, and the three-dimensional structure when we define axial and equatorial. Please make sure you have a clear understanding of that you don't confuse those two. Because it's not a direct relationship. Okay, so back to this. The conformation of the molecule on the right side, where the CH3 group is in more space, more open space, it's stable. It's about 1.8 kilocalories per mole more stable, lower in energy. So if you think about the equilibrium between these two conformations, you'll have more population of the one on the right than the one on the left, and that's defined, of course, by the difference in energy, the actual ratio. And a space-filling model, this shows you why. So again, take a look at the side chair view and looking from the top down on the molecule. You can see that this methyl group is pretty crowded with these other hydrogens, that are axial on the same side of the ring. We refer to that as a 1,3 dioxyl interaction because they're spaced 3 carbons apart. Okay, and then the other ring flip, notice the methyl group is oriented out in the equatorial position, how much more space it has and how much less crowded it is. So hopefully this gives you a good idea about why one would be less energy or more stable than the other. Okay, I'm going to stop there today. We'll take another close look at several other derivatives of cyclohexanes on Thursday and look at those energetics. And then we'll probably start talking about the next chapter, alkenes.